What's up, guys? Today I want to go over the packet that was handed out in lab, and hopefully you have it. And it's basically a big packet full of formulas, and we need this packet in order to get through this course, because nobody is going to memorize all the formulas in this entire packet. So this video is just going to give a brief breakdown of what to look for, how this is organized in the course, where it is in the course if you don't have your packet sheet, and how we're going to be progressing from chapter to chapter. So I guess where we can start off is there's our Ohm's law wheel, and at this point we're going to be using all 12 formulas in some manner depending on what circuit we're working on. But I want to briefly go over this page. In your chapter book, chapter 11, and I'll actually put this here, chapter 11 is going to start talking about some real funny things. E max, E instantaneous, the sine of an angle, and it's going to give you a few formulas on how to factor different values. Now, if I had to summarize this, there are some confusing things in this that are going to really throw you for a loop, but I'm going to summarize this kind of simply. E max really means the peak voltage or the maximum voltage produced on the sine wave. Instantaneous, which you can see right here, E instantaneous, is the voltage produced depending on the angle of rotation. So if I've got 360 degrees of angle, I'm going to have a different amount of voltage produced or induced depending on the angle of rotation. And then the sine of the angle is exactly that angle that is in rotation depending on where that is in 360 degrees. So we have to understand that we're going into a course that's talking about AC power, and we produce AC power through a rotational motor. So when we're using that rotational motor to produce electricity for us, we're using it in a sense that we're inducing voltage based upon 360 degrees of rotation. So if you saw my video on magnetic induction, you clearly saw that I was inducing voltage into a wire, and I was able to turn a light on, and the closer I got to that magnetic field, the greater the induced voltage was and the brighter the light became. Well, now we're going to take that similar concept and we're going to apply it to a rotational magnetic field, and that's why these formulas are there. So that's chapter 11. I want to stress chapter 11 has breakdowns and how to enter this into your calculator. This is where we're getting into the meat of the matter, where you're never going to be able to get through these calculations unless you physically do them in the book. So we'll go over this later in a different video. If I turn this page, now I can see that I have another heading called peak, RMS, and average values. I'll be going over this in a separate video, but these are where the formulas are. So if I wanted to change peak, if we look at this really close, if I was given values in an equation, if I wanted to change peak value to RMS, I would take that peak value and multiply it times 0.707. If I wanted to change my peak value to an average value, I would take that peak value and multiply it times 0.637. That's how this chart works. If I wanted to take peak value, change it to peak, I would just take that peak value and multiply it times 2. And so on and so forth. There'll be another video with an actual calculator breakdown. This particular piece of this packet sheet, and this is, once again, this is in Canvas as well. This is what we did in series in parallel in Theory 1. All these are Ohm's law formulas in a pure resistive circuit, and it's just a reminder of your series resistive circuits, what the formulas are. So there's the series rules and the parallel rules in a purely resistive circuit. So this should not be anything new. We know this stuff, and we know this. If I turn the page, now we're getting to some new stuff, and we're going to actually start off in the classroom this week coming with pure inductive circuits and the rules that apply to those pure inductive circuits. And if you can see this sheet, we now have some new formulas. You're going to need these because nobody has memorized all of these. I will be talking about these in a different video, but this is where you find these formulas in your packet sheet. So when we start breaking these down and we do the activities for them, you have to know what type of circuit that you have. Is it a purely inductive circuit? Is it a series inductive circuit? Or is it a parallel inductive circuit? And here is now the new symbol that we'll be working with. This is the symbol of an inductor. So understand that, you know, we'll be talking about this before we go back to some of the old rules. On this sheet, you also have pure capacitive circuits. So let's show you what the symbol for that is. Pure capacitive circuits, well, is it a series or is it a parallel? This is the symbol for a capacitor. And obviously that's a series, and this is a parallel. These are the rules for those series, and these are the rules for the parallel. So you really got to know, based on the picture, what you're dealing with. So if the picture shows 3 capacitors in series, and if it gives you some givens, you have to come here and see what the rules are for capacitance in series and in parallel. And then probably one of my favorite sheets is the resistive inductive series sheet. There's actually another set of formulas, so this is part 1 and part 2 is on the back side. I have an AC power source. There's my AC sine wave. I have a resistor, and I have an inductor. Resistive, inductive. There's only one path for current to flow, so it's a series circuit. So you should know, when you look at these pictures, resistive, inductive, series circuit just based on the drawing. What's interesting about this is we've got other quantities that we've never seen before. Other names. We have the total column, we have the resistive column, and we have the inductive column. Notice in the total column, you still have voltage, you still have current, but now you have what's called Z. I don't know how well you can see it on this camera view, but Z is going to replace R. Before we had EIR. Well, now we're going to have EIZ because impedance is all of the resistive properties in a circuit, and that is now your total. Z is actually replacing RT from our last course. We had P before. P in our last course represented power. I already taught you that another way of looking at P is VA. Volt times amps equals power, or watts. Then we're going to be solving for power factor. That's a percentage. Show you how to do that. And then we're going to be finding the angle theta, which is another thing that's going to probably make you nuts, but it's just a function on the calculator. I'll explain that in a different video. Notice the resistive quantities haven't changed from the last course. We have voltage dropped across the resistor. We have current across the resistor. We have resistance, and we have power. So the resistive column stays the same. But now we get into this inductor. Here's a symbol for the inductor. We have what's called inductance, or the inductor value, represented by L. We have voltage dropped across the inductor. We have current dropped across the inductor. And then we have X sub L, which means inductive reactance, which is going to replace R from our last course. Inductive reactance is a resistive measurement. So just look at it as EIR. And then VARS is a power type of measurement. We'll learn about that. Hopefully you get ahead of me and do that in your reading. But that's going to be measured, and we're going to calculate that through a formula based upon what is given in this column. And I'm going to teach you that stick to the column. So when you get 2 values in any column, solve for all the others based on what's inside that column or inside that area. So stick to your columns. And then we've got some ugly formulas down here, as you can see. So we're going to spend quite a bit of time on resistive inductive series circuits. If we flip our page, you can see that these formulas continue. Resistive inductive series circuits, there's more of them. Then we get to resistive inductive parallel we've got all these formulas. Once again, resistor, inductor, but now these are in parallel. So something I might add is the series and parallel rules still apply. So if current's the same in a series circuit, it's going to be the same in a resistive inductive circuit. It's not going to change. If voltage is the same, in a parallel circuit, well, then you would end up carrying that same voltage across both columns as well. So those rules are going to come in handy. Turn our page, we have more resistive inductive parallel circuits continued. Sorry about that. Then we get into resistive capacitive. So here's a resistor, here's a capacitor. We'll learn about that. Same thing, same formulas, same type of setup. You're going to be looking at different formulas. You're going to find which formula fits the missing value. We flip our packet again. Resistive capacitive series continued. Then we get to resistive capacitive parallel. More formulas. Then we get to resistive capacitive parallel continued. So we got more circuits in the parallel end of it. And then last, certainly not least, we're going to talk about resistive inductive capacitive series. So watch my pencil. Resistive inductive capacitive series circuits. We've got a few of those formulas. Then you've got more of them continued on the next page. Then, of course, parallel. Resistive inductive capacitive parallel. Resistive and inductive capacitive parallel circuitry. We've got a ton of formulas. And we've got some ones that are continued on the back. And then to finish off the course, we'll be possibly talking about transformer calculations, which look a lot easier than what we were just in. So I want to summarize this up again by saying you need this sheet. If you don't have the sheet, then let me show you what you could look into. Let's get me back. In your course, at the bottom of your course page, sorry about the noise. At the bottom of your course page in AC Theory 2, you have all of these formulas, AC Theory formulas. And they're in the order that the book is. So if you lose your packet, which I know you will, somebody will, all of these are there. You just have to know what you're looking for. So everything that I just went over from front to back is here. All you have to do is, let's just say you were looking for series inductive stuff or resistive inductive. We'd click on it and it's a copy of what you have, and then you could zoom in or not and understand what circuit you're working on. This is in the course. You're going to need it. There's no other way of saying it. There's a lot of things in this course that need to be read. Primarily, just to kind of go back a little bit, Friday we're starting off with magnetic induction. And then there'll certainly be more stuff, but we're going to eventually get to chapter 11. And you have to be able to go through these chapters piece by piece. We will cover chapters 10, 11, 12, 13, 14, 15, 16, and 17 in extreme great detail. So when you come to class on your lab day, you likely will be doing no lab for the next 2 weeks because a lot of this stuff we need to do in class, and I have to make sure that you're up to speed or you'll fail. It's pretty simple. So come prepared and make sure that you're ready and you have everything you need. The next time you are in class, you have to make sure you have all of these sheets and this. See you at the next video.